All right, so we've been discussing stability and looking at what happens for parameters or in general what happens to 2x2 systems and just general systems in general. Sorry, linear systems in general. So we've looked at systems of linear equations that we can write in this form. A is a square matrix, so it's n by n, which means x has n rows. We are now going to look at a very special case of what happens when we have a 2x2 system. And the reason we're going to look at this is because we can figure out in advance what's going on, because the determinant and finding the eigenvalues is easier than the more general case. So just in this case, we know we're going to have lambda 1 and lambda 2. And we know that if both are real, then there's three situations. If both are negative, it's stable, and we have a sink. Both are positive, it's unstable, and we're going to call that a source. And finally, we have one negative, one positive, so it's going to be unstable, and we call that a saddle, because it's going to grow in one direction and decay in another direction. If both are complex, and we know they're going to be complex conjugates of one another, we know two situations. If the real part is negative, we're going to have oscillations, and it's going to be decaying to zero, so it'll be stable. Otherwise, if the real part is positive, it's going to oscillate and be unstable. And so the question we're going to ask now is, in the 2x2 case, we know we can write the matrix as A, B, C, D. Can I just figure out what's going to happen based on some properties of this matrix? And the answer is going to be yes. Just if you give me A, B, C, and D, it's going to turn out, we can tell immediately what's going to happen in terms of our stability, and we're going to be able to figure out which of these 5 cases we have. So, and we're going to start out by just grinding out things the hard way. So we're assuming we have a 2x2 system, and the matrix looks like A, B, C, D. And the stability is going to be determined by the eigenvalues. So if I take that matrix and I subtract lambda from the diagonals, so I have A minus lambda, B, C, then D minus lambda. If I take the determinant of that set equal to 0, that's going to define my eigenvalues. So I multiply the diagonals to get A minus lambda times D minus lambda, then minus B times C. All right, let's expand that out. So I'm going to get AD minus D lambda minus A lambda plus lambda squared. So I FOILed that out. Subtract BC. Let's collect like terms. So I've got my lambda squared. My lambda terms are going to look like minus A plus D lambda. So it's minus A minus D all times lambda. So I factored out the minus 1. And then what am I left with is plus AD minus BC. I can immediately look at this and say, that's AD minus B. That's the determinant of my matrix. A plus D is the sum of the diagonals. It turns out in practice that that's an interesting quantity for a matrix, and something that pops up. We're going to give that a name. We're going to call that the trace of the matrix, and it's the sum of the diagonals. Okay, so what do we have? We have, for our equation to solve for lambda, we have lambda squared minus the trace of the matrix lambda plus the determinant of the matrix all has to be 0. And so just knowing the trace and the determinant, I can solve this to get my values for lambda. Just to make this easier, I'm going to call the trace T, and I'm going to call the determinant D. So I'm now working with 0 equals lambda squared minus T lambda plus D. And knowing the trace and the determinant is going to tell me what the values of lambda are. In particular, if I use the quadratic equation, I get lambda is going to be minus a minus T plus or minus. Minus T quantity squared is going to be T squared. Minus 4 times 1 times D is minus 4D, all over 2 times 1. So I'm going to have lambda 1. Let me be careful. I want to stay consistent with my notes. So I'm going to call that the plus version. Yes, so the lambda 1 is going to be 1/2 of T plus square root of T squared minus 4D. And lambda 2 is going to be what happens when I subtract the square root of T squared minus 4D. And just as before, I have 5 situations I've got to deal with. First situation is when T squared minus 4D is negative, so these are complex. And then I can just focus on the real part. And then the other situation is when I get lambda 1 and lambda 2 both negative, a case where one is positive, one is negative, and the other case where they're both positive. So I'm going to have to deal with these 5 cases. I'm going to do the complex one first because it turns out to be a little easier. So I always try to do the easier part first. It gives you a little confidence and a little traction. And then it helps prepare you and gives you some insight into what's going on for the more difficult point. So I'm going to first look at the complex case and look at the real case. Notice this depends on 2 things, T and D. And so the idea is if you give me T and you give me D, I can try to figure out where this is going to happen. And so basically there's 2 things I have to deal with, and I'm working in 2 dimensions. So I'm going to basically partition a plane. We're going to call the trace determinant plane. And I'm just going to arbitrarily make T be the horizontal axis and D be the vertical axis. And if you give me T and D, that's going to give me some point here. And I want to basically divide this up into regions. And you give me T and D, I can immediately see which region it is in, and then tell you exactly where you're going to be in these 5 cases. So the question is how do I do that? So we have a linear system that we're writing. It's a 2 by 2 case. Our matrix is A, B, C, D, X. I know that the trace is A plus D, and the determinant is AD minus BC. That implies that my first eigenvalue is going to be 1/2 quantity T plus the square root of T squared minus 4D. And lambda 2 is going to be 1/2. And I take T minus the square root of T squared minus 4D. And case 1 is if I have complex valued roots, and this is going to either be stable or unstable. Regardless, I know it's going to oscillate. All right, so to be complex, I know that T squared minus 4D has to be negative. And if I factor out a minus 1, or think of it this way, if I multiply both sides by minus 1, I'm going to flip that. So I'm going to get 4D minus T squared is positive. So for my lambda 1, I can think of this as negative 4D minus T squared. So this becomes 1/2 T plus 1/2. Now if I factor out the square root of minus 1, so I leave the 4D minus T squared alone, that becomes an I. And likewise, I'm going to get a negative of the same thing here. So my lambda 1 and my lambda 2 look like that. This is my complex thing part, and my real part of both of these things is 1/2 t. So I can immediately see that if t is negative, it's going to be stable. And if t is positive, it's going to be unstable, because the real part is basically just 1/2 of that. So what does that mean? So again, I've got my system of equations. My lambda 1 is 1/2 t plus the square root of t squared minus 4d. Lambda 2 is 1/2 t minus the square root of t squared minus 4d. So I know that t squared minus 4d is negative, which means that t squared is less than 4d, so d is greater than 1/4 t squared. And I know that if t is negative, it's stable, and if t is positive, it's unstable. And I just said before, I'm going to look at what happens for given t and d. I can think of those as two different numbers. So it's like a horizontal and a vertical axis. D being greater than 1/4 t squared. So if I plot d equals 1/4 t squared, so anywhere along that parabola, d is equal to 1/4 t squared. If I pick a point above that, that means d is greater than the 1/4 t squared. So that means this is going to be complex. So anywhere above this parabola, I'm going to have complex eigenvalues. If t is less than 0, it's going to be stable. So over here, I'm above the parabola, and t is negative. So this is going to be stable with oscillations. If I'm over here, I'm above the parabola. My t is positive, so this is unstable, and it oscillates. That's a mess. Let me redraw that just to make this more clear. So what did we just say? We said that if I draw d equals 1/4 t squared in this plane, oops, I used green above, in this region here, t is less than 0, d is greater than 1/4 t squared, it's going to oscillate and be stable. In this region here, this is going to extend all the way up. What did we say? We have d is greater than 1/4 t squared, t is positive, so it's going to oscillate and be unstable. So that takes care of all the complex cases. Notice I've got 1, 2, 3, 4 more regions to work with. So this is going to be a little tricky because there's only 3 more cases to deal with. So immediately see where it's going to be a little complicated, what's going to happen. Okay. So where are we now? We're still with a 2x2 system. Derivative of x is equal to a times x. A is a, b, c, d. My trace is a plus d. My determinant is ad minus bc. I'm now focused on the real case. So in the real case, we know that, let's just write down my lambda 1 and lambda 2. Let me be consistent here. We said lambda 1 is 1/2 t plus the square root of t squared minus 4d. Lambda 2 is 1/2 t minus the square root of t squared minus 4d. So this means that t squared minus 4d is positive, which means that t squared is greater than 4d, so d is less than 1/4 t squared. So that means we're underneath that parabola we just saw. And again, that's feel good because it's basically everything else. If that didn't happen, we'd have a problem. Now, the other thing to notice is that the way I've constructed this, square root of something is always positive. Square root is defined to be a positive number. So if I have plus a positive number, here's a minus a positive number. By design, lambda 2 is less than lambda 1 because the thing in the square root is positive. And the things I wanted to look at were the case where they're both negative, one's positive, one's negative, or they're both positive. So my three cases are both are negative, which implies that if I show that lambda 1 is negative, lambda 2 is going to have to also be negative. So for this case, I only need to show lambda 1 is negative. For the second case, 1 is positive and 1 is negative. So that implies that, lambda 1 has to be positive and lambda 2 has to be negative. So I'm going to have to show both of those cases separately. So those are two things I need to show, that lambda 1 is positive and lambda 2 is negative. So that's going to be hard. And then in the other case, they're both positive. So if I just show that lambda 2, that's wrong, they're both positive. So that means, so what did I say? Lambda 2 is less than this. If they're both positive, it has to look like that. Sorry about that. But if I show that lambda 2 is positive, lambda 1 is also going to have to be positive because it's bigger. So for this case, I only need to show that lambda 2 is positive. So here's what I'm going to do. I'm going to do this case first. I'm going to do this one second, because this, I think, is going to be easier. This is going to be the next easiest. I'm going to do this third because it looks like it's going to be the hardest. But hopefully by doing these two first, it's going to show me what's going on here. Okay, so case 1. I want to show for what happens, what are the conditions for lambda 1 to be negative. So that means 1/2 t plus the square root of t squared minus 4d is negative. And I already know, because I'm assuming things are real, that d is less than 1/4 t squared. Right, which means that t squared minus 4d is positive. Multiply both sides by 2, doesn't change anything. So let's see, I know this is positive. So if I subtract t from both sides, I get that. The thing on the left is always positive. The thing on the right could be positive or it could be negative. So I need to be very careful here. So what is going on here? So the thing on the right is going to be equal to some value. And it has to be, and I'm looking for values of the thing in the square root. They're going to fall below there. Right? So it's going to basically be, I'm going to be careful here. So I've got this backwards. Let me back up. I want to make sure I get this right. So what do we have? We have lambda 1 is negative. T squared minus 4d is positive, which means that d is less than 1/4 t squared. I'm assuming lambda 1 is negative, so that means that's 1/2 of the quantity t plus t squared minus 4d is negative. Multiply both sides by that. Let's do this. I'm going to go the other way because I tried subtracting that and it got a little confusing. Let's go the other way and see what that implies. So if I subtract t from both sides, does this offer me more insights? Now notice this thing on the left, this has to be positive. And for this thing on the right to be bigger, means that minus t has to be greater than 0. So I immediately see that t has to be negative. And now if t is negative, minus t is positive, and now I can just square things and not worry about flipping signs. So t squared minus 4d has to be less than t squared. And if I subtract t squared from both sides, I get minus 4d is less than 0. Divide both sides by negative 4, so d has to be greater than 0. So I have that t is negative, d is positive, and from here, I know that d is less than 1/4 t squared. So those are my three conditions. So what did I have? I had d equals 1/4 t squared. In this region here, we have oscillations, unstable. Here we have oscillations and it's stable. This is the case where it's a sink. Both eigenvalues are negative and real. So d is positive, so that means I'm going to be either in this region or this region. But t is negative, so that means I'm going to be in here, and I'm below this parabola. So if you give me a value of t, I know the value of d has to be between 0 and this parabola because it's bigger than 0 and less than this. So I've just marked out this whole region. And so in here, it's going to basically be a sink and it's going to be stable. Okay. Let's look at the case where they're both positive. So this is case 3. So I know that lambda 2 is positive, lambda 1 is positive, and I know that lambda 2 is less than lambda 1. So if I show that lambda 2 is positive, lambda 1 is automatically going to be positive. My lambda 2 is 1/2 t minus the square root of t squared minus 4d. So I already know that t squared minus 4d is positive, which means that d is less than 1/4 t squared. So I'm forcing this to be positive, and that has to be true. So I'm underneath the parabola. So I multiply both sides by t. So then I get this is greater than 0. Let's do this. So let's add this to both sides, because then I'll have something positive on the right-hand side. So if the right-hand side is positive, it's the square root of something, this has to be bigger than this, so this has to be positive. So this immediately implies that t has to be greater than 0. So I can square both sides, no problem. It's not going to change anything. So now if I subtract both t squared from both sides, I get 0 greater than minus 4d. So d has to be greater than 0. So what do I have? I have t greater than 0, d greater than 0, and d is less than 1/4 t squared. All right? So coming back now to my regions in this plane. By the way, because it's the trace and the determinant, we call this the trace determinant plane. Up until now, if we plot t equals 1/4 t squared, we're going to have oscillations and it's unstable. in this region. It's going to be oscillations and stable in this region. Here it's going to be a stable sink. And now, so if t is greater than 0, we're to the right. If d is greater than 0, we're above. So it's somewhere in d, here or here. But I know that for any point in here, d has to be less than 1/4 t squared. So this region is in here. And we know this is going to be unstable. Both eigenvalues are positive. So it's going to be a source. And the only thing we haven't dealt with yet is case 2, where lambda 2 is negative and lambda 1 is positive. And I am going to hope beyond hope that it's basically everything for d negative. And that'll basically fill in all possibilities for t and d. So, case 2. Lambda 2 is negative and lambda 1 is positive, and I know this has to be true because lambda 2 is less than lambda 1, and this is the case where 1 is positive and 1 is negative. And I know this is real valued, so I know that t squared minus 4d is positive, which means that d is less than t squared over 4. Lambda 2 we said was 1/2 quantity t minus the square root of t squared minus 4d. Lambda 1 is 1/2 quantity t plus the square root of t squared minus 4d. So this means that 1/2 t minus the square root of t squared minus 4d has to be negative. And here's the key thing, is this is and. Both of these things have to be true. 1/2 of t plus the square root of t squared minus 4d is positive. All right, so for both of these, I can multiply through by t, which means that the thing in the parentheses has to be less than 0, and the thing in parentheses over here has to be greater than 0. All right, let me add t to both sides. Yeah, we do that. So this is t less than square root of t squared minus 4d. And now let me subtract this. Same thing. Let's just keep this consistent so that I've got this thing over here. What does this mean? This has to be positive. Square root of something, by definition, is always positive. This quantity is the same thing as this, but here it's negative. So if t, so this says t is less than square root of t squared minus 4d. This is t has to be greater than the negative of that. So t has to be between these two things. So if this is my t, I know, oops, sorry. I know that t has to be between, somewhere between these two values. So that means when I square it, t has to be less than what's going to be on either side, right? So let's look at this. If I square this, t squared has to be less than t squared minus 4d. Because this is negative, and this has to be above it, then t has to be less than this when I square it, because otherwise, so how can we think about that, is, right, so I've got square root of t squared minus 4d is some value here. And now that means that if I pick values in between here and here, they're always going to be below it. So that means this same thing has to be true when I square both sides. And notice because this is squared, this has to be greater than 0. So now I can subtract t squareds from both sides. So I get minus 4d has to be greater than 0, which means d is less than 0, and that's exactly what I was hoping for before. So my two conditions are t has to be less than t squared over 4. Notice that has to be positive, and d has to be less than or equal to 0, or less than 0, which overrides. So if this is true, that automatically has to be true. So that's my only condition. So let's go back to my trace determinant plane. What have we shown? So if I plot 1/4 t squared, I've got a region in here. In this region, I'm going to have oscillations, and it's going to be unstable. I have a region in here. In this region, I'm going to have oscillations, and it's going to be stable. And then what we saw before is in this region, it's going to be an unstable source. And in this region, we saw that it's going to be a stable sink. And what we just showed that is if d is negative, we're going to have lambda 1 positive and lambda 2 negative, so it's going to be a saddle. So anywhere where the determinant is negative, I get a saddle. So that's basically everything below the d equals 0 line. So this is going to be this region below here, and in here we have d less than 0, which means I have a saddle, so it's unstable. And that's going to be true over here as well. It's going to be a saddle and unstable. So why do I go to all this trouble to look at this? It's because now, suppose you give me a differential equation, system of equations. Suppose the matrix associated is 2, 4, 1, 3. It's 2 by 2, so which means I can use this. The trace is going to be 2 plus 3 is 5. The determinant is going to be 2 times 3 minus 1 times 4, so 6 minus 4 is 2. D is positive. I immediately see it's not going to be a saddle. Okay, so I can immediately rule out that immediately. I see that T is positive. So T is positive and D is positive, so I'm in the first quadrant, so I know it's unstable. It's either going to be oscillating and unstable, or it's going to be a source. And to decide whether or not I'm above or below this parabola, I just have to compare this to 1/4 t squared. Okay, so 1/4 t squared is going to be 1/4 of 5 squared is 25 fourths. So that's going to be what, 6 1/4? Is that correct? I believe so. And D is 2, so 2 is less than 6 1/4. So that means I'm somewhere in here. So this is an unstable sink. And the only thing I did was take a trace in the determinant, and knowing the trace determinant plane, I can tell you exactly what's going to happen for the stability of this awful thing.